last time, I think we have talked about the kinetic chain reaction, and we are continuing to discuss about the initiation, propagation, and termination reactions. And we discussed that we have induction period in this initiation reaction, and propagation is very rapid, and you have repeating in many the same steps, and undergoes finally the termination reactions. We have to assume that at this steady state, the initiation and the termination is about the same, and we need to eliminate the radical concentration in terms of the known variables and known constants later on in order to calculate the overall rate of polymerization reactions. So the chain cross polymerization is different from step cross polymerization reaction in terms of when you obtain your high molecular weight components, and that's the very main difference between the chain growth and the step cross polymerization reactions. Well, we need to compare about the initiation and termination reactions before we go over to the final polymerization reactions. Okay, if we can compare the radical initiation and the ionic initiation, it's a little different, although we are in the category of chain cross polymerization reactions. Okay? Now, for example, if I have a monomer, which is called the isobutylene, you have a vinyl group here, and one of these carbon has two methyl group instead of one methyl for propylene. Okay? If you have two methyl group here, it's called the isobutylene. If I have isobutylene and it's attacked by the initiator, for example, the peroxide radical, if you have a radical attacking the methyl group, and if one of the methyl group is attacked by the radical, then you form the radical here. If I have a radical, then the neighboring double bond has two electrons distributed over to two carbons. So one of these electrons will be moved over here to form this double bond here, okay? So that you form the radicals. So this is what they call the conjugation. Okay? Conjugation. In other words, if I have a radical, then this radical should attack the other monomer, okay? The other monomer to form the polymerization reactions. But instead, if I have a radical attacking this one of this carbon, the methyl, and forms this methylene radical, neighboring this double bond will form the conjugation reactions. So you form this type of the conjugated structure. So if I have a conjugated structure, these electrons are distributed over to three carbons, okay? Three carbons, in other words, 1, 2, and 3. So instead of attacking this other monomer, the electrons are moving right here, residing right here, so that you do not proceed with the radical initiation reactions in the case of isobutylene. Okay, so the radical initiation, although you have the right initiator, depending upon the type of the monomer, it will determine the polymerization reactions. So in the case of isobutylene, you never see the radical polymerization, but instead you have ionic polymerization reactions later on in chapter 10. Okay, so type of the monomer is very important. So what I have emphasized here is that the ionic initiation is different from the radical initiation. The ionic initiation will initiate the components which contains the ring. So ring opening polymerization is possible in the case of ionic polymerization reactions, but rather if you have a ring containing monomer, then radical initiation is not possible. Also, if I have an isobutylene type of the monomer, you will not be able to proceed with the radical polymerization reactions, but rather it performs the ionic polymerization reactions. So free radical and ionic reaction is a little different. And particularly if I compare free radical versus the ionic polymerization reactions, and in terms of the ring opening, if I have a ring, the anionic polymerization is possible for the ring opening polymerization reactions, whereas radical, as I said in previous slide, is not possible. Now, end group of your chain end also influences the ionic versus the free radical. But in the case of free radical, this is quite true radical. In other words, you should have a radical in there. But in the case of ionic polymerization reactions, your chain end is anionic or cationic depending upon the type of the reactions. And this is much more complex than these free radical polymerization reactions because we are dealing with the ions. Okay, the ions are not just to stay as a single sole ion, but you should have a counter ion. Okay, in other words, if I have a positively charged ion at the end of a chain, it's not staying just a positively charged ion, but you should have negatively charged ion as a couple, right? As a couple, or vice versa, right? So the strength between the positively charged ion versus the counter ion or Gegen ion or whatever you call is very important. The strength is very important between the positively charged chain end and Gegen ion. Okay? Now this is strength, bond strength, depends upon what type of your monomer that you are using, what type of your salt, what type of your counter ion that you are using, or what type of your solvent that you are using. So it's much more complex than free radical polymerization reactions. So here we call for example, if I have an initiator called the Al+ or aluminum tetrachloride, depending upon what kind of Al, what kind of methyl group, or what kind of propyl group, what kind of alkyl group that you have a different strength in the cations. Now, degree of association is the bond strength between these positively charged and negatively charged ions. Depends upon solvent system that you're using, stability of your end group, okay, and the type and the size of your counter ion, Gegen ion, or the temperatures. So, all of this degree of association affects the reaction rate, overall reaction rate, overall the termination rate. Therefore, the polymerization, degree of polymerization, of course, and the stereospecificity. In other words, it determines whether it could become a cis transfer. I think we will talk about this stereospecificity, but anyway, the components that has in the space will be affected by the degree of association as well. Now, termination reaction is bimolecular. In this case, free radical polymerization reactions, whereas cationic is unimolecular, and the anionic reaction is a leaving polymerization reactions. Okay? Now, unimolecular versus the bimolecular is that whether you have two molecules in your reactants or one molecules in your reactants. If I have two molecules combined together to become one molecule or two molecule, whatever, depending upon the combination or disproportionation, it is called the bimolecular. So you should have a two molecule at the reactant side, in the left-hand side, in your case. If I have a one molecule, okay, in the reactant side, reactant position, then it's called the unimolecular combination, unimolecular reactions. So we will see what's the difference between this cationic and the free radical in the slide, next slides. Now, what I'm saying about the bimolecular reaction is that if I have a free radical termination reactions, okay, I think last time we talked about the coupling or combination or disproportionation. Okay? Now this is the scheme about the difference between combination and disproportionation. For example, if I have a radical growing chain, okay, with a radical, another growing chain, at the end of the chain you have a radical. So one of these it's not just a monomer, but it could have some kind of repeating units. So at the end of a chain, you're one of these chain end radical, the other one meets together to become coupled or combined to become one molecule as a terminated species. Your molecular weight will be doubled, right? Now we have two molecules in the reactants, so we call this as a bimolecular reactions because two molecules are involved in the reaction. Okay? Whereas in the disproportionation reactions, we have one radical and the second radical, which is the same, so bimolecular reaction. But the disproportionation is different from coupling because two growing chain, two kinetic chain becomes two physical chain, okay? Two physical chain. Now the mechanism of this disproportionation is that we have a covalent bond, radicals, electrons, but you have a C and H, which is regarded as a covalent bond. Is the same as this one, okay? I think we need to remove this CH here. But anyway, if I regard this as a C, two electrons of each from carbon and hydrogen, and one of these hydrogen radical is removed, okay? Removed, and one of these hydrogen radicals is removed, so that the other radical is combining together along with the another radical from carbon to become double bond. Okay, become double bond, and one of this H dot will be moved to here to become CH. Okay. I know it's very complex, but this C and H is two electrons. Okay? One of this electron will be moved to here from this another radical will combine together to become double bond, and another one, the hydrogen radical, will be moved to here to become this CH bond. Okay? So this way, we have a two physical chain from two kinetic chains, and this kinetic mode is called the disproportionation reactions. Okay, so the KT again is KTC plus KTD, as we have described already last time. Okay? Now this is regarded as a bimolecular reaction because regardless of the final number of molecules that you produced, okay, you have two molecules involved, and this is what we call the bimolecular reactions. What about the cationic terminations? Okay? Cationic termination mode is that you have cations, carbocations at the end of your chain. Okay, although we describe this as a plus XY minus. XY minus is the XY minus is a Gagenion or counter ion. Okay. But actually, there is no pros. Actually, there is no pros because this carbocation is combined with X and Y. Okay? So this is one molecule instead of two molecules. That's why we call this as a unimolecular reaction. And the termination reaction mode is that one of these XY will be cleaved. X and Y, in this case, is aluminum tetrachloride here, and the chloride ion will be moved, whereas AlCl3 will be moved over to here as a Y, and this the X would be a Cl group here. So you form the terminated species with the Y minus ion instead of the Y itself. So you form the final terminated species from one molecule. This is what we call the unimolecular reactions. Anyway, we will talk about this in detail in the next chapter. But this is the combination reactions. But what about the disproportionation reactions? Disproportionation reaction can also be formed that you have a double bond formation from the hydride elimination, where the one of this is H minus ion will be moved to here. H plus proton release. In other words, CH. I have a CH. So if I have a proton release from this beta carbon, what it is that we have a so proton will be released, leaving the electrons into the carbon, second carbon, and it will be moved to X and Y, so that you form double bond. So this will be moved to here. Two electrons will move to here to form the double bond. So you have a double bond. With the H, Y, and X, okay? So this way, you have a proton release to form the double bond. But in this case as well, you have a unimolecular reaction because we have only one molecules involved in the termination reaction mode by the disproportionation in this case. Anionic termination is about the same. So you have a one molecule, and hydrides are eliminated from here to form the double bond. Okay, and one of the metal, the carbocation will be reacting with the hydride to form the hydride metals. Okay. Anyway, you have a one molecule, so this is also called the unimolecular reactions. Okay, if we can summarize again, the overall reaction rate is that in the case of ionic polymerization reactions, this is the unimolecular reaction, whereas a free radical is a bimolecular. Reactivity of each the radical versus the ionic polymerization is different. Reaction rate is much higher in this case. Okay, reaction rate is much higher. And the free radical compared with the free radical reactions. So this is about 10 to the 4th to about 10 to the 5 times higher than or faster than the free radical polymerization reactions. Chain transfer is always occur in the case of free radical polymerization reactions, so you should be very careful. Whereas anionic polymerization, there is no chain transfer reaction unless you add the water as a terminating species. One of the disadvantages of this, the ionic polymerization, is that the purity of your monomer and purity of your solvent, particularly the presence of water, are very important. So you should eliminate any residual, the moisture or the small amount of water content in the solvent in the monomer anyway. So it should be very difficult to proceed with the anion polymerization reactions. We will talk about this polymerization system at the end of your chapter, but the free radical, the polymer can be formed in a variety of forms. Okay, whether you have a solvent or not, you may proceed with the free radical polymerization without any solvent. Okay? But you should have an initiator, of course. Initiator and monomers are essential parts. But if I have a solvent, then it's called the solution polymerization. If I do not have any solvent, that's called the bulk polymerization. And if I have an emulsifier, that's called the emulsion polymerization reactions. And if I have a suspension reaction with the water, with a small amount of the soap or detergent, that's called the suspension polymerization reactions. And all of them, the free radical polymerization is possible with a variety of type of polymerization systems where anionic and the cationic polymerization reactions, you cannot use the emulsifier or the suspension polymerization reactions. So there are some differences and limitation in ionic polymerization reactions, but in order to form the block copolymer, you have to proceed with the ionic polymerization reactions. Okay, so so far we have compared with the ionic polymerization versus the free radical polymerization reactions, and also we talked about the polymerization reaction versus the non-polymerization reactions, and we also compared what's the difference between free radical versus the ionic in terms of terminated spaces, in terms of initiations, and the type of reactions. Now, from now on, I think we will go over to the free radical polymerization reactions, and we will derive the radication, okay, because we are talking about the kinetic chain reactions. Kinetic chain always contains the radicals, okay, or active species to form the physical chain. Now, let's talk about the initiation reactions. Initiation reactions, again, we need to have an initiator, okay, initiator. It becomes radicals. So last time we talked about the R dot. R dot is about the same as I dot, okay, here, and it becomes a 2I dot. That means you have symmetric components of initiator, and it's broken into two species with the same amount of the molecular weight and so on, and it becomes a radical, which is described as a decomposition of the initiator. So initiator decomposition is the first step. So the rate constant for this initiator decomposition is called the KD, decomposition rate constant. And if you add the monomer here, then one of this initiator radical will attack this monomer to become primary radical species, and the initiation rate constant is described as Ki. And Ki, remember, is very small. Okay? It's about 10 to the minus 2 to 10 to the minus 4 liter per mole sec. And here, although we add the initiator may not 100% participate in the radical polymerization reactions. If you have about 100 initiators, and about 50% of your initiator is participating in the radical polymerization reactions, we call this as the initiator efficiency factor is about 50%. Okay? So we describe F, initiator efficiency factor, F, and it could be 1, which means initiator will 100% of the initiator will participate in the polymerization reactions, where if initiator efficiency factor is about 0.5, you lose your 50%, whereas another 50% will participate in the polymerization reactions. So now I will explain to you why our initiator is not participating 100%. Right? Anyway, we have our KD and KI here. And remember the KI and KD. Now, why we do not have 100% initiator participate in the reaction? One of the reason is that cage effect. Cage effect. Okay? Initiator. If you have an initiator, you have usually have a monomer, an initiator, and solvents. Solvents are surrounding these initiator molecules. And the initiator, although it forms the I dot, if the I dot is surrounded by the solvent molecules, there is no chance to meet the monomer, so that I dot will lose its activity, and could chain transfer to the solvent molecules, and you lose your initiator efficiency. And that's one of the reasons, which is called the cage effect, and it's called the primary recombination. And in that case, initiator, although I dot is formed in the cage of the solvents, I dot will be combined together to become I2. Okay, I2 will become I dot, but it becomes combined together as primary radicals in the solvent cage, rather than I dot attacking the monomer, so you lose your efficiency factor. It could become, recombination is possible as well. So as I said, you have recombination, and in some cases, elimination reactions will be occurred within the cage. Okay, within the cage, in other words, peroxy radical will become methyl radical, or evolving the one molecule of CO2. This methyl radical will combine together to become ethane, or methyl radical will attack this peroxy radical to become some strange components, methyl acetate. Okay? And in this case, you have a dead space, and although you have two radicals in the reaction site, two radicals are becoming a dead end species, dead species, rather than attacking the monomer. Okay? Instead of attacking the monomer to initiate the monomer and to become polymerization reactions, it just stays in the dead species, so you lose your efficiencies within the cage. Okay? So with this, all possibility of recombination and the elimination reactions, the efficiency factor is not 100% usually. Second reason might be that, which is called the secondary combination or induced decomposition. Let's say that we have R radical. Okay, R radical. You form the initiator decomposition, and you form the R radical or I dot. Okay? And I dot will attack the. If I dot will attack the monomer, it initiates and propagates. But I dot, instead of attacking the monomer, if attacks the initiator, for example here, and then you form the it takes the hydrogen and forms the dead end species, and you have a radical. But this radical species will become some components like this, and this overall reaction is that although you have one radical and one initiator is expected to form the two radicals. So we expect from this reactants 3 radicals attacking the monomer, but it forms only one radical at the end of your chain and the end of a reaction. So overall reaction is that you're expecting to have 3 radical species, 1 from radical, 2 from initiator, okay? But you only have 1 radical. So you lose your 66%, okay, 66% of your efficiency from these reactions. And this is what we call the induced decomposition, and this might be the second reason that you may not have 100% efficiency of your initiator. And third reason, another possibility of induced decomposition is that you may have a chain transfer to the solvent. If I have I dot will attack the solvent, which contains the active hydrogen, and forms this dead spaces. And dead spaces, as a solvent radical, may attack this I dot, will become only I dot. So you lose your efficiency of your initiator with the same analogy with the previous case. Okay? So with this, from this reason, we lose efficiency of the initiator, one by the Kg effect, second by the induced decomposition. Okay? That's why we have to think about the F. Okay? Your F will be determined and maybe given to you when you're given the problem sets or in the exam, that F might be 0.8 or 0.9 or something like that. Okay, the third reason of the induced decomposition is that I dot will attack this M, and this IM dot will attack this I2 and becomes the I dot, and which is the same as the previous cases, just changing the solvent and the monomer in this case. So we have to think about the efficiency factor, and the efficiency factor is usually ranging from 0.5 to above 1. Okay, so let's go back to the radiation. Okay? Now, if you remember the radiation, Ri is equal to Ki times I dot and M. Okay? Now, why? We have our I dot and M in the reactants with the Ki. So Ri here is equal to Ki times I dot and M, okay? Right? But we have to think about the F, and should include F here, but I dot and M, and if I go back to the previous case, this is I2 and KD, and you form the 2 I dot, so you can replace this as well. And it will become the F, which is the initiator, the efficiency factor, and it will become, I think it's KD, okay, KD times I2 with the 2. You form the 2 radicals from one initiator, so the 2 will be the convention. So I think this should be a KD. And M dot will later on here. This is the formation of the M dot. M dot will be, it doesn't matter whether it has only one monomer fragments or the long, monomer fragments. So it doesn't matter the size of the molecules. I will just describe this M dot as any components which contains a radical, okay, regardless of its size. So F could be a 1 or it could be less than 1. Let's think about the last 2 statements. If you have a large amount of monomer, okay, do you think the initiator efficiency factor will be increased or decrease? If I have a fixed initiator concentration, okay, let's say 10 molar, and you increase your monomer concentration from 10 molar to 100 molar. Do you think initiator efficiency factor F will increase or decrease? Increase, yes, increase. Yeah. You have many monomers with a given initiator concentration, efficiency will be much faster, much higher. If you have a large number of initiators and small number of molecules, you lose the efficiency of your initiator. Okay? So this describes what will happen in terms of the concentration monomer and initiator concentration with the efficiency factor. Now, what is the type of the initiator that we are using? Usually, initiator contains OO, peroxide, posulfide, and azo group. Okay, azo group. N is not just NN, but should contain N double bond N. Azo groups instead of NN. For example, I think we saw one of the initiator called AIBN, azo isoputronitrile, AIBN. But what about the peroxide containing monomers, the initiators? We have acetyl peroxide. You have acetyl group. This is called the acetyl CH3CO. You have two CH3CO with the peroxide group. Okay. So this is called the acetyl peroxide. We have a benzoyl group, two benzoyl group with one peroxide. Okay, why benzoyl? This is called benzoic acid. Okay, so this term is called benzoyl. So the benzene and CO is called benzoyl. We have two benzoyl groups with one peroxide. So this is called benzoyl peroxide or BPO. Terminated, abbreviated as a BPO. If I have a benzene with the isopropyl units, then that's called the cumyl. We have a cumyl peroxide. Okay. Now the number here, temperature, here below this name is the decomposition temperature. So if you increase your temperature to the temperature that's written in here, 80 to 100 or 80 to 100, 120 to 140, then it will become two radicals, decompose in the peroxides, okay, and becomes two radicals because of the symmetric structure of its initiator structures. So it's not very high temperature. It's around 100 degrees C. So initiator with the monomer, if you heat it up to about 100 degrees C, it starts to form the initiation reaction and proceed with the propagation reactions. We have another the initiator called the tertiary butyl peroxide. This is the tertiary butyl group. Okay, tertiary butyl groups with the peroxide, which is called the tertiary butyl peroxide. I have hydroperoxide as well. This is a C, not double bond, but COOH. Okay, COOH, which is also the peroxide. Whether it could be a tertiary butyl peroxide or cumyl peroxide, peroxy acid, which is a little different from the tertiary butyl peroxide. I have the AIBN, which decomposes into two. So the AIBN has the much lower temperature for decomposition and becomes two radicals as well. So with this initiator, you form the I dot or Al dot. So I dot will attack this monomer and becomes IM2 and containing the because I dot already contains M, okay, so it becomes IM2, IM3, IM4, stuff like that, and becomes IMN dot. Okay. This is called the propagation reactions, and termination reaction occurs by combination or disproportionation. So two kinetic chain becomes one physical chain in the case of coupling or combination, whereas two kinetic chain containing two radicals at the end of a chain of each species will become two independent physical chains in the case of disproportionation reactions. So KTC and KTD here. Now if we write the rate equation, it becomes the monomer consumption rate. Monomer consumption rate is Kp times I dot concentration or M dot concentration here, and M concentration with Kp. Okay? Right? And termination reaction is that the rate of consumption of this M dot, rate of consumption of this M dot is equal to KTC plus KTD times M dot concentration to the second, and we put this 2 because two molecules put it together as a convention. Okay. So Rt and Ri, we derived Ri, Lp, and Lt. Okay. What about this is the convention, because the two radicals are eliminated and participate in the reaction, just in the case of decomposition reactions, in the case of initiator. What about the overall rate of equations? Overall rate of equation is Ri plus Lp and Lt, but Lt is very small compared with the Kp, and also Ki is very small. So overall reaction rate is determined by or governed by rate of propagation reactions, Lp. So we can rewrite this overall reaction rate is equal to Kp times M dot and M. It's very simple. Kp times M dot and M, and your question might be why we have derived the Ri and Lt. Okay, because we already have Ri and Lt, and your overall reaction rate is determined by propagation rate. What happened? Well, Lp is Kp times M dot and M. So Kp is a constant, M is a constant, or non-variable because we put this monomer from your intention. So you know this M variable, but we do not know, and it's not easy to determine this M dot, because the radical concentration during your reaction is difficult to, although it will be possible, but it's difficult to determine this M dot because it's too fast. Okay, I think we have described here the radical concentration M dot is difficult to measure, although it's possible to measure, but it's not easy. And because the concentration of this radical is very low, so that in order to determine this radical concentration, what we should do is that we put this radical species, put it into nitrogen at a low temperature, like a minus 190 degrees C, and then ship to the resonance measurement system called ESR, electron spin resonance, and measure the electron spin in the magnetic side, and determine the concentration. But it's not easy, and it's very tedious. Therefore, it will be much desirable to eliminate the m dot, okay, with a known and useful variables or constants. So although it's possible to measure this radical concentration, it's not practical. So we would like to replace this m dot with the known concentrations. Well, question is how we can eliminate this m dot with known concentration. Remember that we talked about the steady state assumption, right? Steady state assumption. At the steady state assumption, Ri is equal to Rt. Okay, we derived Ri and Rt. Now we use this Ri and Rt with the known terms. So Ri is described as 2FKD here, not instead of Ki. I2 instead concentration of the initiator is equal to Kt Rt 2 times Ktc plus Ktd times m dot to the square. So from this reaction, these Ktc, Ktd, and I2 and Kd, everything is constants or known variables with only one unknown and undesirable parameter. So we can rewrite this m dot with although a little complicated, it's possible to describe this with the constants. Okay. So Rp, as we have described, not rho. I just try to replace this with a p, but it's not law, not symbol, but the p. Okay, propagation rate constant or polymerization rate constant is Kp times m to the m dot. So if you replace m dot with this one here, you can rewrite with this equation. So rate of polymerization is determined by Kp with some constants, okay, some constants with m, which is monomer concentration, and initiator concentration to the half. Now, I have told you that the decomposition rate constant is about 10 to the minus 2 to 10 to the minus 4. Propagation rate is higher than this one. Kp is about 10 to 2 to 10 to 4. And Kt is even higher. Remember that we have 10 to 6 to about 10 to 8. Okay? Now I ask you the question, what happened? All because we have a higher termination rate constants, and the polymerization should not be possible if you linearly think about your reaction rate constants of each cases. But as we derive this equation, Kt is in the denominator instead of denominator. So it doesn't matter whether you're a larger rate constant of termination versus the little smaller the propagation rate constant and the initiation rate constant. Okay? You do not need to remember this equation, but you take your cunning paper with this equation. So always think about this. Okay? You can take your cunning paper if in the exam, okay, with this equation. But please make your note of this. So overall, we derived Ri, Rp, and Rt. Okay, and Rp is very important, and Rp is very simple because I dot or m dot attacking the m will become m dot or becomes mn dot, right? So rate of polymerization Rp is equal to the Kp times the monomer concentration m with a bracket times radical concentration, m dot. So m dot will be eliminated by the assumption, which is called the steady state assumption, and Ri could be equal to RT, so that you can rewrite this m dot with the known concentration and variables and replace them. Okay, so this is possible. Usually the RP, rate of polymerization, is linearly dependent upon the concentration of your monomer. If you add much more monomer in your reaction system, polymerization rate will be increased linearly. What about the initiator concentration? Initiator concentration to the half or the root is always linearly dependent upon the rate of will determine linearly to the rate of polymerization reactions. Assuming that you have a constant which is slope, okay? So if I plot Rp versus the initiator concentration, if I have a linear slope, the slope will be m, Kp, and others, right? So in the previous literature, if I have a methacrylate as a monomer using the BPO, benzoyl peroxide, as an initiator, you have a linear relationship between Rp and I2 to the square root. Okay? So slope will be something that I have described to you in the previous equations. Right? If I use a vinyl acetate with AIBN, isobutyronitrile, you have a linear slope. Okay? Linear slope, although the slope is different with a different system, with a different monomer, a different initiator, but it's linear, meaning that you have different Kp and different constants, because this will determine rate constants are a little different depending upon your polymerization systems with the different monomer and initiators. Again, the BPO will become 2 radicals. AIBN will become 2 radicals as well. In some cases, square root dependency may not be correct. Okay? Now, in this case, we have very good linear systems, but we may not have the linear dependencies. In some cases, the styrene with the benzoyl peroxide with the benzene as the solvent system, Rp, the rate of polymerization is dependent upon monomer concentration and I2 to the square root. Okay? But in some cases, if I change the solvent from benzene to toluene, rate of polymerization will be dependent upon monomer concentration to the square root times the monomer concentration. So it's to the, in some cases, it changes a little bit. And why? Because the toluene containing the methyl group will influence the induced decomposition of your initiators. Okay? So benzene system and toluene system will affect the initiator efficiency factor and the decompositions. So the monomer concentration will be changed in this case as well. So although I described the ideal cases of the rate of polymerization with the known rate constants, it may be a little bit changed in your textbook and in their future advanced textbooks, so that you may see a little bit of a deviation from the standard cases. Okay. Okay, so we described the rate equations. Okay, Rp, and Rp is very important. We knew that Rp is not just a simple cases, but with the steady state assumption, we can describe the Rp as known constants and known variables with the monomer concentration and initiator concentrations. Now, we can talk about the molecular weights, molecular weight or repeating units, or degree of polymerization, or kinetic chain length. Chain length is molecular weight, of course. So we can talk about the kinetic chain length at a steady state assumptions. At the steady state assumption, or if you think about the steady state assumption, Ri is equal to Rt, and we can manipulate these equations. The kinetic chain length is defined as the average number of the monomer molecules that was consumed or to participate in the polymerization reactions, divided by the each radicals. If I have one radical, then it's just one. Okay? If I have 10 radicals at the chain end, then I'm counting the 10 chain ends. Okay, so in this case, the KCl is equal to Rp or Rp divided by Ri or Rt, because at the steady state assumption, Ri is equal to Rt. So KCl is defined again as Rp divided by Rt or Ri. And we knew that Rt is equal to Rtd plus Rtc. Okay? Now, for coupling reaction, which is RTC cases, the rate constant, the KTC is half of the concentration in the case of disproportionation, because one polymer is produced from the two growing chain. This is not polymer, but growing chains. Okay? Two growing chain will become one molecule, one polymeric molecules. So by convention, we put just a half of here. Okay? Whereas in the case of disproportionation reactions, we just two growing chain will become two radicals. Two growing chain will become two physical chains. So it's just the same. Okay? So RTC and RTD could be described as Rp divided by Rt, and RTC is Rtd plus half of this RTC. And you can manipulate this equation to here so that it will be rearranged to become 2Rp divided by Rt plus, the 1 plus Rtd divided by Rt. And Rtd divided by Rt here could be defined as rate of or portion or fraction of disproportionation in your termination reactions. And this is described as Y here. Y. So if I rearrange this equation, KCl is 2Rp divided by Rt square of 1 plus Y. Okay? If there is if Y is equal to 1, meaning that your termination is governed 100% by disproportionation reaction, it will become 1, so you can cancel this out. So KCl is defined, determined by the rate of polymerization reaction divided by the rate of termination reaction, but depending upon the termination mode by combination or disproportionation, your molecular weight is different, your kinetic chain length is different. Okay? So if you have 100% disproportionation, then that Y is equal to 1, so that it becomes Rp divided by Rt. And if Y is equal to 0, meaning that your disproportionation reaction, the ratio is 0, so the combination reaction is combination termination is governed, then the KCl is 2 times Rp divided by Rt. Okay? Therefore, the DPN, the degree of polymerization, degree of polymerization. If I have a coupling reaction, coupling is governed in your termination. And if I define the KCl mu here, now this proportionation reaction is governed. dPn is mu, whereas coupling, in the case of coupling cases, 100% coupling, dPn is 2 mu, okay? Because you have two growing chain mixed together to become the double your molecular weights. Okay, so this is the description of what we have done, and we can describe this the rate of polymerization reactions, which was just described in a minute. Okay? Now, we knew that monomer consumption rate is Rp, polymer formation rate or termination rate is RTD plus half of this RTC. Okay? So degree of polymerization or the degree of polymerization is determined by Rp divided by, I think we have already derived this equation number 1, and Y is the fraction of disproportionation in your termination mode, and therefore, if I define mu as a kinetic chain length, okay, and dPn is equal to 2 mu divided by 1 plus Y. Okay? If Y is equal to 1, meaning that you have 100% disproportionation, dPn is equal to mu. Okay? If I have 100% coupling, this Y is equal to 0. So the molecular weight will be double the kinetic chain length. Now, you know that equation number 2, which we have just described, and remember that at steady state assumption, RT is equal to Ri. Then if I combine this 1 and 2 and 3, dPn, depolymerization reaction, is a little bit complicated reaction, but it's becoming number 4, equation number 4. Right? Or we can describe this with Rp here. You can describe this equation as 5. So number 4 and number 5, you can should put this equation in your cutting paper as well. Number 4, equation number 4 is the equation that you can describe. You can calculate the degree of polymerization with a known monomer concentration and initiator concentration and reaction rate constant of each decomposition, the termination, and the propagations, with even the initiator efficiency factor. Right? So, equation number 1 here, or excuse me, 2, equation number 4 is very important. If you look at the equation number 4, monomer concentration is linearly dependent upon, linearly influence the degree of polymerization reactions. So if you add more monomers into your reaction system, your molecular weight, of course, will be increased. Or degree of polymerization will, of course, increase, right? However, if I add more initiator in your reaction system, each species of initiator, okay, will add the monomers with a less amount. So degree of polymerization will be inversely related with the degree of polymerization reaction versus the initiator concentrations, right? So this is what I can describe about the kinetic chain reactions. And have any questions?